Okay, we have seen how to add a marker to the model. We've seen how to add a muscle to the model. Let's now see how we would add degrees of freedom to an existing joint in the model. The knee is the best place to demonstrate that, I think, because most OpenSim models have a 1 degree of freedom knee, where the only free and independent motion of the knee that is defined in the coordinates here is knee flexion there, right? You can't see it here because they're not listed on the coordinates and because it's kind of subtle motions. But while it's flexing and extending the knee there, it's actually doing other rotations and translations of the knee too. They're just coupled to this knee flexion motion, right? There might be situations where you may want to have free and independent motion of the knee other than flexion here. You might want to allow the knee to adduct and abduct in the frontal plane or internally and externally rotate in the transverse plane. Right? For example, if you don't want to force everyone in your study to have like this particular neutral alignment of the knee, or you want to include like motion of those non-sagittal rotations that may not necessarily be coupled strictly to the flexion motion. There's a lot of reasons why you might want, or a lot of situations where you might want to define a knee here with more than 1 degree of freedom here. Again, the best way to do something like this, to make a change like that to the model, is to find another example where that's already done and copy it over and then adjust it to have the specifics be suitable to what you're trying to do. The hip is a good example here, where the hip can flex and extend, but it can also adduct and abduct, and it can internally and externally rotate, right? And those adduction, abduction, internal, external rotation motions, they're not coupled to hip flexion at all, right? They're free and independent motions. When I flex the hip here, it doesn't internally, externally rotate the hip at all, right? It doesn't adduct and abduct the hip at all. Those are uncoupled motions. They're free and independent motions. So how do I change my knee to have those 3 free and independent rotations that my hip has there? Let's first check out what the hip looks like. So I'll go to my joint set, and it starts with my pelvis relative to the ground. I don't really care about that here. So let's scroll down and find my hip. So there's my hip, and it's got a parent frame, pelvis, and a child frame, femur. That's just saying this joint exists as the femur relative to the pelvis. Then it defines the 3 coordinates that I'm going to use to specify the motion of those 2 frames relative to each other: hip flexion, hip adduction, hip rotation. Okay. The only numbers here that's really important are this range here. That's the minimum and maximum range or positions that coordinate can take on. You don't have to worry about those too much. It's not specifying like what's the physiological range of motion at this joint for this model. All it's really doing is setting the bounds on this slider on these coordinates, the range that you're allowed to like manipulate them over graphically when you're manipulating it here. So you don't really need to worry too much about like what specific values you punch in there. It's mostly just a graphical thing. Okay, so my hip here has 3 coordinates defined, and it's also got these 3 independent motions here, right? So my knee, since it's just got knee flexion, I'm going to expect that it probably just has 1 coordinate defined here, something like hip flexion. So I'm going to copy these other 2 coordinates. And then I'm going to scroll down here to my knee, which should be the next joint in my list here. Yeah, there's my right knee. It's called Walker knee because the paper that the knee model here is referencing, the first author's last name was Walker, like Walker et al. 1975 or something like that. So that's why it's called Walker knee. Okay, then I go down here to my coordinates for my knee, and like I expected, it's just got that 1 knee flexion coordinate, right? So I'm going to paste in those other 2 coordinates, and I don't want them to be hip adduction. I want it to be knee adduction, and I don't want it to be hip rotation. I want it to be knee rotation. And these ranges don't matter that much here, but I'm just going to arbitrarily make them, it can go -1 radian and +1 radian for adduction, abduction, and then -1 radian, +1 radian for internal, external rotation. Again, those are not realistic physiological ranges of motion for those, 2 particular motions in that particular joint. Again, that's just the range that it's going to allow me to visually manipulate them here over in my graphics here. So don't worry too much about what those values should be. It's not really specifying anything super important in the model in most situations. Okay, let's load my model back in here and see if I'm done already. That would be nice, huh, if it's that simple. Okay, so there's my model. Let's get a good look at its right knee here. Go to my coordinates. And excellent, it's now got knee adduction and knee rotation. And I uh-oh. Didn't do anything. It's broken, right? Did my screen just freeze here? No, I can still move it. And I can still flex and extend. It's not quite as simple as just naming those coordinates, right? Me, as like a kinesiologist and a biomechanist, I know what knee adduction is. I know what that motion means anatomically. OpenSim on its own isn't smart enough to figure that out, right? It doesn't know that because I defined knee adduction here that, oh, that means I want you to, when I change that value, you know, rotate my knee in the frontal plane there. It doesn't intuitively know that. I have to tell it those things. And you tell it that down here in spatial transform, and that's where it defines the 3 potential translations and the 3 potential rotations that any particular joint can undergo. If you look back up in the kind of top level tag for most of these joints, you'll see that it's custom joint. And that's the definition that you use a lot of the time when you want to define a joint that has like an arbitrary number of degrees of freedom, right? You might have all 6, you might have 1, you might have 3, you might have any number between 1 and the full 6 degrees of freedom. A custom joint can have any one of those. Where you tell it how many is down here, again under spatial transform, where I say here's the rotations it can do and here's how they're defined, here's the translations it can do and here's how they're defined. So the difference here, the reason that my knee is not moving in the frontal plane there, but my hip is because my hip has that transformation defined, my knee doesn't. So let's go up to my hip and see what that looks like. So I can see here under spatial transform, it's got hip flexion defined about some axis according to a linear function. Okay, now what does that mean? It says when you change the magnitude of this hip flexion coordinate, that causes a rotation about this axis, you know, moving one reference frame relative to another reference frame, about this axis according to this function. Okay? I don't have a deep understanding of this linear function here. It's one of the many things in these models that I didn't make the model, I didn't make the software, so I don't have a really deep understanding of what exactly it's doing a lot of the time. But my understanding, and the best way that I've been able to figure out by playing around with these, is that what this definition here is saying is take this value of this hip flexion and do a 1-to-1 mapping between the magnitude of that coordinate and the rotation about that axis. So if I change this hip flexion coordinate magnitude by, say, 0.1, that causes a rotation about this axis of 0.1 radians. Okay? This 0 here, I think that's like some sort of baseline offset. Like that's kind of defining like when the hip flexion coordinate has a value of 0, you know, what's the relative translation or what's the relative positioning, generally speaking, between these 2 reference frames defining that joint about that axis. Well, that's also in its 0 position. If you wanted to offset that and make it something other than 0, and when the magnitude here is 0, you could change that to something else. But typically, we just see that left as 0. Okay, so that's what my hip looks like for flexion. It's also what it looks like for adduction. It's coupling that coordinate, the magnitude of it, to rotation about a second different axis, again with that linear function. Okay. So then let's go down to my knee. And for its flexion motion, it looks like I expect. It's basically the same as my hip flexion motion, right? It says for knee flexion, if you change that, perform a rotation about some axis there, and do it according to this linear function, right? But then I go down here to my second rotation, and that doesn't look much like my second rotation for my hip, right? It's got knee flexion there again, even though it's not the knee flexion motion that's about that axis. It's got a different axis, and then rather than that linear function, it's got this spline function there. So what's going on there? What this is doing is it's saying hip flexion, that occurs about this axis. That's the sagittal plane axis of the knee. Okay. Knee flexion. That's I misspoke there. Sorry. Knee flexion, that occurs about this axis, the flexion axis of the knee. Knee frontal plane motion occurs about this axis, but it's defining that motion as a function of knee flexion. That's what this spline function is doing down here. It's saying these x values here, when the knee flexion angle takes on those values, assign the rotation about this adduction-abduction axis these y values for those magnitudes of those rotations, right? So it's coupling the knee flexion motion to the knee adduction-abduction motion, right? It's making the adduction-abduction angle a function of the flexion-extension angle. That's some of the data that's in that Walker paper I mentioned a little while ago. It specifies how those non-sagittal motions and rotations of the knee are typically coupled during just like passive flexion of the knee to that flexion-extension motion. Okay. So it's probably hard to see here, but while the knee is flexing and extending here, it's actually subtly adducting and abducting itself as well. And that's probably hard to see here. So to kind of exaggerate it, I'm going to go into this output of this spline and just increase all of them by a factor of 10 to make that a little bit easier to see. Okay, and let's reload our model here. And then get a good look at my knee in the frontal plane there. And here you should hopefully see when I do knee flexion, you get this very exaggerated frontal plane motion of the knee. All right, so all I did there is kind of magnify how strongly the adduction-abduction motion is coupled to the knee flexion-extension motion. Right? So this is basically saying, imagine somebody's like flexing their knee when they're walking. It would be forcing the adduction-abduction motion of the knee to be this prescribed function of that flexion angle. So when it's a subtle motion like it was before I magnified it by 10 there, it's assuming everybody's knee kind of moves along that prescribed path in those non-sagittal motions as a function of that sagittal motion, which of course is not strictly the case. But it's probably more realistic than just assuming those angles are always 0 all the time, which we know for sure is not the case, right? So there's a lot of modeling decisions that kind of come down to decisions like that. Do you want to entirely leave out something that you know is there, or do you want to include it in a prescribed way that you know is imperfect and is not strictly correct for everyone? I kind of lean towards the latter, adding that detail that I know is happening qualitatively, but I'm maybe not quantitatively including it, right? Rather than the former, which would be assuming that the knee adduction angle is always 0 all the time when everybody's walking, which I know for sure is incorrect. The alternative here, at least in some modeling workflows, would be to not couple those motions and just define knee adduction as an independent motion from knee flexion, similar to how hip adduction is an independent motion from hip flexion. Okay. So to do that, I go back to my spline here, and rather than making the transformation between this knee flexion coordinate and this adduction axis, that prescribed function of knee flexion, I change that rotation to be a function of that knee adduction coordinate, and then I make it a linear function, just like my flexion was. Then let's reload our model. And zoom in there. And now when I manipulate knee adduction abduction, you can see now I get independent knee adduction abduction. I don't have to flex and extend the knee to get adduction abduction. I can do it on its own, independent from knee flexion. Now you lose that coupling, right? Now when I flex the knee, it's just flexing the knee. It's not adducting, abducting it at all. I've now defined those as independent motions. Knee rotation still does nothing because I haven't defined that. So let's go back to my model. And under knee rotation, I'm going to change that. Rather than being a prescribed function of knee flexion, I'm going to make it its independent coordinate. And rather than having a spline function that defines it, I'm going to make it that linear function. And then load that back in. And zoom in one last time here. And now when I change my rotation, then I have independent internal external rotation of my knee. Okay, so that is how you would go about adding degrees of freedom to an existing model like a 1 degree of freedom knee to make it a multi-degree of freedom knee.